Welcome in. Magnetic field, and then the force, which is the result of that magnetic field. So that's exactly what we want to be able to talk about in this video. Now, my assumption is that you have studied the introduction to magnetism at some point. So you're going to be running into magnetism. You've done it before. You have seen, for example, the right-hand rule, although I'll explain it again in here. But you have seen these things so that they're not completely new to you. Okay, so I'm going to put up a link up above there to the introduction. So I highly encourage you. You can watch the videos I've created, okay, on the grade 11 content for electricity and magnetism. And my assumption is this is the video that follows that. All right, so what is the goal in this video? Well, we want to be able to find out what is the force that is caused on a particular charge. So that charge can be both positive or negative. And the cause of the force is a magnetic field. This charge is actually moving. So it is moving at a certain velocity that you have. Please note, this is the one key distinction between, for example, forces that are caused by electric fields and forces that are caused, for example, by gravitational fields. Both of those forces are parallel. Okay, so that's number one. They're parallel to the actual field itself. So gravitational field or electric field. Also, if you have, let's say in the electric side, if you have charges, if you have one charge, it can be stationary and it can feel a force from, for example, charges that are surrounding it or an actual field, okay, that might be surrounding it itself. And that actual charge indeed doesn't have to move. In a magnetic field, if the charge is not moving, so if its speed is 0, then there is no force that is acting on it. So it has to move. So that's one thing that you should note, and hence that's why we have the actual velocity. Now, this velocity that we have in here is a vector. Now, the other thing that is a vector is, of course, the magnetic field. Now, this magnetic field can be caused, okay, by all kinds of different items, and that's on the introductory side. I'm not going to talk about the causes of the magnetic field here. I'm just going to assume that there is a magnetic field, and we, from now onwards, are going to designate a magnetic field, okay, with a vector force, and it's going to have, okay, the capital B assigned to it. This is for historical reasons. So don't fret if you see this capital B. Okay, it means it's a vector. It's the magnetic field that is present. And it is uniform. So it's unchanging. It's hard enough already when you're getting introduced to these concepts. So we will assume that it is uniform, and that's exactly what you do in your grade 12 or introductory physics sides, okay, at least in the beginning. So here is your magnetic, okay, field, which is uniform. We want to be able to calculate what the force is. Now, when you're looking at this equation, you might say, what in the world, okay, is this? Okay, because this looks like a multiplication symbol between two vectors that you have. It is not a multiplication symbol. Now, in most physics courses, this formula will not be introduced at all, and all you're going to see is this formula. Now, there's a key distinction between these two. Now, the reason why professors or teachers don't introduce you to this, because they are uncertain, okay, if you have been introduced to this concept, which is known as a cross product. Now, if you've taken vectors in grade 12 or possibly maybe in grade 11 or introductory side, then it is 100% worth it, okay, to understand the cross product between two vectors, because what it does is the result here is going to be a vector that you have. Q, remember, is just a charge. It's a scalar. It's just a numerical value. But these two are vectors. And the cross product, I'm going to put a link up above there. If you're a keen student, I highly encourage you to take a look at that. If you are not keen, okay, if you're running out of time, you don't necessarily have to see this formula within here, but I wanted to introduce it here so that you know that this is really the true formula that you have. And this equal sign is actually incorrect. This, which you do see in numerous textbooks in physics on the introductory side, most of the time the magnitude symbols will be dropped. So here I keep the magnitudes because of what I want you to know, that this is the magnitude of Q. Of course, it can be both positive or negative. This is the magnitude of your velocity. So this is just the speed. This is the magnitude of your magnetic field. But all these have actual vector values. But we just want to know the magnitudes. That's what you have in here. Why do I say that this right here is actually not an equality? Because if you take a magnitude times a magnitude times a magnitude and you multiply it by sine of the angle, which I will explain, then you're going to just get a scalar value out. And in this case, it's going to be, okay, so as you have it within here, you'll see that it's going to be a positive value because this angle is going to be the smallest angle between these two vectors. All right? So, therefore, this result is an actual vector, so it gives us a direction. Here, this just gives us the magnitude of this vector. And if you want a direction, you're going to be using your right-hand rule. Okay? So you're going to have to be using your right-hand rule to find out in which direction it is pointing. Now, a little bit about the actual units. Of course, the unit for charge is coulombs, at least the standard metric unit. Okay, the unit charge for velocity is meters per second, against metric standard units. But this, because you haven't maybe seen this in the past, this, okay, is actually given or defined, okay, in terms of the units of Tesla. Yes, it is the Tesla. It's a famous scientist, although most people now know Tesla as a company. Okay, it is named after the scientist who worked on these, okay, and it is named after him, just like we named Newtons and joules and pascals, etc. But 1 Tesla is equivalent to kilograms per coulomb, okay, per second that you have there. So if you ever want to think about what a Tesla is, that's exactly what it is, and we'll define it at that. If you want to know more information, you can certainly look it up, but I won't go beyond this. So now we know all of the units within here. Sine of an angle. Of course, you should be familiar with sine if you're watching this video. All right, so what is next? Okay, so as you're going through this, okay, you're going to have 2 vectors and you're going to have a charge. And you are after simply what is the force. So before I dive in, okay, so as we're going to go through the step-by-step process of finding out what that force is and then what its direction is. So what I want you to know is this, that you have a velocity and you have an actual vector field, in this case magnetic field, and they're pointing in some directions. Now they're going to be in 3 dimensions. Now, for the moment, okay, let's simplify it, because they're always going to be in some plane, which is 2-dimensional. So if they're 2-dimensional, this is what we have. So let's imagine that we have some charge Q. This charge Q is moving at a velocity vector, say in this direction. Doesn't matter what direction that might be. Now, we have a magnetic field. Now, that magnetic field that you will see is going to be, okay, let's say, for instance, okay, so that magnetic field is going to be present, and we would duplicate, so I'm going to just duplicate so that you can see that this magnetic field is present everywhere, okay, as this charge is going through. So it's present just like a gravitational field, okay, is present anywhere you are, okay, around, for example, the Earth's surface. So if you wanted to know, and this is your magnetic field that you have, it's not a singular vector, right? It's a field of vectors that you have, but they are uniform. So that's what we would have. So if you want to find out and relate it back to this equation, so it's not very difficult to think about what the actual magnitude of the charge is. Okay, it's not difficult to think about what the magnitude of the vector, the velocity vector is, that would be the speed. Okay, and it's not difficult to figure out if we are given, and most of the time you will be, given what is the strength. So we say the strength of the magnetic field, how strong it is. Just like a gravitational field or electric field, how strong is that? So here we have the strength of this magnetic field. Now, that angle right here, so this special item which you haven't been necessarily introduced to in the past, we need to know what the angle between these two vectors are. Now, how do you do that? So you can imagine, so this is how I imagine this. I always take only one of these, and to make my life simpler, all right? And then what I'm going to do is it's like I am not seeing these at all. Now, of course, they are present, but, okay, I can do this right there, where this is my, of the velocity, this is my vector field of my magnetic field that I have. And what you are interested in is you are interested in the smallest angle, okay, between here. That's what you want to be able to know. So this is our angle that we have. So that's our theta. And what we want is we want sine of theta. And now, of course, depending on what sine of that angle is, okay, it will take a certain component, okay, of these two vectors, and it will scale them by this, right? So that's what we would have in here. Now, if this angle, okay, by the way, because it can be anywhere, so it can be, you know, very acute, okay, it can be much bigger, it can be also obtuse. So now here, a little bit note on when it is obtuse. So what happens in this situation, okay, so as you're going through, which angle should you be going through within here? So you always will be choosing the smallest angle. So please don't choose, because you can of course think about this angle right here, okay? But you're going to choose the smaller one of the two, which means that our angle is going to be less than 180 degrees, okay? Or in radians, less than pi, okay? And it's going to be between 0 and 180. That's what it's going to lie, okay? Right there, that's what you will have. And notice that sine of 0 and sine of 180, so if the vectors are parallel, then sine of the angle is 0. So there is no force present on a charge, even if it is moving, if it's moving exactly in the same direction or in the opposite direction, so parallel to the magnetic field itself. So that is a note on angles for you, all right? So with that being said, now let's take a look and see how we can utilize this through this step-by-step process. This is what I do. So first off, if we have the magnitude, that magnitude can be found by simply multiplying the charge, the speed, the magnetic field strength, and then the sine of the angle. If you have all of that, you'll find out what the magnitude of the force is. Now, step one, what if I wanted to find what the direction of it is? Because force has a direction. And that will utilize the right-hand rule. So first off, you will point your fingers in the direction of motion of the charge. So wherever the charge is moving. So what do I mean? Okay, so this is if you were introduced to the right-hand rule. Okay, so your fingers are going in the direction of how the charge is moving. Okay, so that's one. Now, the next thing that you do is you move over and you take a look right here in which direction, okay, is your magnetic field pointing. And you will curl your fingers. So you will curl your fingers, okay, towards the magnetic field. So therefore, as you take this in, you will curl your fingers. So as they are pointing in this direction, you will then curl them in this direction. So if your right hand is pointed so that it only allows you to curl in this direction, that's the wrong way. So you have to twist your arm around, okay, so that it points, and then you can curl your fingers towards this. This is how I take a look at the actual magnetic fields. So in this case, as you see there on the screen, okay, so I'll put a picture, okay, up above there so that it shows you how you are curling them in. And if you are curling them in, what it's going to tell you is that the direction of the force is in the direction of your thumb. So your thumb is telling you, okay, the direction of the force. So in this situation, as you curl your fingers through, this would be, well, in this plane, it would be out of the plane, okay, right here, which we designate in this way. So it's coming out of the plane, okay? So in your video, okay, so if you're looking at it, okay, it's pointing in out of the plane, All right, so that's what you would see there, and that's exactly what you see there on the screen in terms of the image of my hand being curled all around. Now, one little note. If the charge is positive, okay, then the direction is in the direction of the thumb. If the charge is negative, then the direction is opposite. All right? So if this charge, which is moving right here in this direction, but that charge was a negative charge, then, okay, you still follow the right-hand rule, but you're following the right-hand rule on the assumption that it's a positive charge. And then all you have to do is say it's a negative charge, so it's going to be in the opposite direction. So instead of out of the page, okay, it would be into the page. That's what you would have. And finally, to calculate the magnitude, rather simple. Simple. Take the charge, take the speed, take the strength, and then calculate the sine of the angle in between them. That's what you have step by step. Let's take a look at a few examples to illustrate this. So I have created, okay, so here's a set of examples. So here it is. Here's our charge. Okay, so within here, notice I'm putting magnitude. Okay, within here is the actual speed, okay, that you have of your charge. This is where it's moving. That's the speed of it. And then this is the strength, which is 1.5 Tesla, okay, of that. Now, I have labeled, so there's 3 examples in here in terms of trying to figure out and how to calculate these out. So for all of these examples, the magnitudes are the same, okay, and we're going to figure out what all of these angles are, right? So your charge Q is moving, so that's the blue that you see right there, so that's where it's moving. So this is right here, this is in the plane, this is the YX plane right here, so it's in that plane. Okay, this is moving right along the Z axis or Z axis. So all the blues are highlighted within here. Your magnetic field is pointing, okay, so as you see there in the green. That's what you have there. So now, very simply, so if we want to know what the direction is. So again, what I want you to do is take your fingers, okay, point them in. I'm not going to put it on the screen so that you practice this yourself. So this is moving in this direction, this is moving in that direction. Notice that since this is in the y-axis, the actual magnetic field is in the z-axis or z-axis going upwards right there. So the angle in between here is going to be 90 degrees. They're perpendicular to each other. Okay, so sine of that angle, okay, so sine of 90 is going to be 1. So that's going to be an easier one. And now you're going to curl your fingers towards it, so it's going to be curled in this direction. Now, so what does that mean? That means if you curl it in that direction, then your force, okay, if this was positive, is going to be along this direction. And if your actual charge, okay, was negative, sorry, if charge is positive, is in this direction. If charge is negative, it would be in the opposite direction that you have. Okay, so that's what would have been the result. So let's assume for the case number 1, let's say that it's positive. So it would have been in this direction, okay, as you're going through right there. So negative, positive. All right, so this is what you have. What about the strength? Well, all you have to do is now multiply these together. So one multiplied by the other, multiplied by the next. Sine of the angle, so in this case, the sine of the angle is 90 degrees. So this would have been just equal to 1. And I'm going to put the result right there, okay, as I compute it. So that is the result. I'm not going to do any rounding in here. So this is what you would have. Again, and we'll keep that because it's going to have the same magnitudes with the other ones. The only thing that will change is going to be the angle in between there, okay, if there is a change. Now, one note in terms of the units. So again, please note that when you're multiplying your charge Q, okay, is in coulombs, that's in metric standard units, right? Your speed is in meters per second, so it's multiplied by that. And then the Tesla, okay, that you see within there is kilograms per, and that will be coulombs, okay, per second. So this is what you would have. So notice the coulombs would cancel. You would have only kilograms, okay, meters, and then seconds squared, and then déjà vu, this is nothing else but a Newton, right? Because Newton's mass times acceleration, so kilograms, meters per second squared. Okay, so this would be indeed in newtons if you keep it all in metric SI units. So that's the first example. The next example I want to tackle is the one on the far right, which is this one. So notice that your charge that you have within here is going to be pointing in this direction. Okay, so your charge, okay, is moving, in that direction, which is on the z-axis. And notice your magnetic field is downwards right here. So what happens in this case? So this is something that you should know. There is no calculation needed. There's no right-hand rules needed or anything. If your charge is moving either exactly in the same direction as the magnetic field or in the opposite direction, so we say that is parallel to the magnetic field, then the angle between them is either 0 or 180. And as I mentioned, in those cases, there is no force at all. Okay, so it is 0. There's no force which is present. So there's no calculations. Okay, so this example is a really nice one and a very great one to ask students, either multiple choice questions or something of that nature, okay, so that you can see if you understand the concept. Now, the last example, so this one is probably the hardest example. Now, what I want to be able to do is, within here, I just want to be able to project this out. Okay, so the way that it is drawn, so notice here's your x-axis and here is your y-axis, all right? So it is in that plane that your charge is moving and your magnetic fields, okay, that you have. Now your magnetic field is not necessarily in a plane, okay? It's three-dimensional. It's just that the arrows are all pointing, okay, into the x-axis that you have in there. So I want to translate this out. So I want to be able to draw this. So let's draw this out. So this is what we're used to, okay? Which is y, and then here, this would have been your x. So now, if you draw it in this way, so notice here is your x, okay, right here. So it's pointing in this way. So that is transition, so that is pointing you in that way. And then your y, which in this case is pointing you here, so that is actually pointing you that way. So first, let's take a look and see. Notice the magnetic field, which is pointing in the direction, okay, of the positive x. So I'm going to draw that out. So within here, so it's pointing in this direction right there. Maybe let me make it bigger, okay, so that it just pops out at us, okay, a little bit more. There you go. That's the magnetic field that we have, all right? Okay, so that's that green. Now, the blue, which is the movement, so notice it's 50 degrees away from the positive axis, okay, of the y. So that's what you have, but it's moving in this direction, right? So notice that it's moving away from the y. This is the positive y, so that's the positive y, and it is moving away from that, and that angle is 50 degrees. So therefore, if you're going to draw that out just so that it's visually showing us, okay, so this one I don't have to make as big, okay, because it pops out in the second quadrant right here. So this is the speed of that charge, okay, which is moving along right there. And this angle, they're telling us, is 50. So now the question arises, all right, okay, so what happens in this case? And which angle do you take? Now notice this is 90 degrees. So the total angle is 140 degrees, okay, if you are going to be going in that direction as you view it. So with this, we're going to have sine of 140. So please don't, put in here, so it's not sine of 50. It's definitely, not this angle right here. Remember that it's the smallest angle in between the two. So that's what we have right there. And now the direction, you have to point your fingers, okay, into this direction, okay, right there with your right hand. So as you see there on the screen, and you're going to have to curl your fingers. You're going to have to curl your fingers towards this direction with your right hand. And if you do that, then you're going to notice that if the charge is positive, so for a positive charge, it's going to be pointing, so this is for a positive charge, it's going to be pointing into, okay, the page. So within here, as you can see there, it's going to be pointing in this direction right there. So if that's a positive charge as you curl your fingers around. So that would mean, we would do something like this. And if it was a negative charge, that means it does the opposite. It would be pointing out. And in order to find out what the answer is, well, okay, all we have to do is we have to take this number, okay, which is the multiplication of these three, and then we have to multiply it by sine of 140. And that is, okay, let's punch it in. There you have it. So that is the result that you have right there. You hit equals, and you can round to, again, whatever it is that you like. So this is the introduction. It's a long introduction, but I hope that the examples now give you, it's not that hard once you comprehend the right-hand rule, and then you understand that you can multiply these out. So the magnitudes, okay, very easy to find what the force is itself. It's always the angle that's kind of a little bit tricky, so just be mindful how you compute it. And again, for all the keeners, I highly recommend that you learn about this cross product. Okay, it will help you understand exactly what is happening. This just comes from algebra. All right, thanks for watching. See you in a future video. Bye, everybody.